What is an aneroid barometer?
Device to measure gas pressure in which the elastic top of an extremely low pressure drum is bent by the pressure.
What are airships used for?
Since the first airship flight in 1852, by Henry Giffard in France, the dirigible, or airship, was used predominantly for military purposes. In the First and Second World Wars, airships were used for bombing and surveillance on both sides of the Atlantic. Commercial passenger transportation on airships was conducted for only a few years. While today's blimps are used for advertising and for televising sporting events from high elevations.
Why do your ears hurt when you dive to the bottom of a swimming pool?
Just as the weight of the air above us creates atmospheric pressure, the weight of water creates liquid pressure. Close to the surface of a pool there is very little water that can push down and increase water pressure. The further a person dives below the surface, however, the greater the water pressure. The eardrums are especially sensitive to the increased pressure, for they do not have the reinforcement that the diver's skin has. In fact, your eardrums can usually feel pressure when diving just 1.5 to 3 meters, 5 to 10 feet, below the surface of the water. Feet, deep or in the ocean at a depth of 10 meters, 32 feet. Although the ocean contains a lot more water than a lake, it is the depth that determines the weight of water directly over a diver that defines the amount of pressure the diver experiences. Therefore, a diver who is 20 meters below the surface of a lake will experience more pressure. In fact, twice the pressure than the ocean diver experiences at 10 meters. Salt water is denser than fresh water, but the increase in pressure caused by the increased density is small in comparison to that caused by the difference in depth.
What is a pitch?
Like loudness, a description of how the ear and brain interpret sound frequency.
How far will it rise?
As some of the wood rises above the level of the water, the volume and the mass, and therefore the weight, of the water displaced will be reduced. When the weight of the wood and the weight of the water displaced are equal, the net force on the wood will be zero and it will no longer move.
What are examples of wheels and axles?
The screwdriver is one example. The larger the diameter of the handle, the greater the torque that can be applied to the screw. Many examples have a rope or chain wrapped around the axle. A sailing ship's steering wheel could be represented by either the left hand or the center drawing. Depending on whether the helmsman pushed down or pulled up on the edge of the wheel. The rope around the axle is connected to the rudder, which is then turned to the right or left. A similar device would be a device to lift a bucket from a well. The wheel is then replaced by a crank, but the operation of the device is exactly the same. Again, the crank can either be pulled up or pushed down to exert a force on the rope to pull the bucket up. The rear wheel of a bicycle can be thought of as two wheels on an axle. The large wheel has a rubber tire and exerts a backward force on the road, while the smaller wheel is the sprocket that the chain turns. The right-hand drawing above shows that the force of the chain is larger than the wheel's force on the road.
What is an atomic mass number?
Number of protons and neutrons in nucleus.
What is a radioactive nucleus?
Unstable nucleus that emits particles in decay to another nucleus.
How do hippopotamuses sink to the bottom of a riverbed?
Hippopotamuses spend over half their day in the water. In order to eat, the hippo, which can reach almost 3 meters, 10 feet, in length and weigh 10,000 pounds, must sink to feed off the vegetation that grows on the bottom of rivers. The hippo, however, has one major problem: his low density forces him to float at the surface. And he is not agile enough to quickly dive down to the bottom and come back up again. In order to reach the bottom, he needs to increase his density. So the buoyant force cannot supply a large enough force to keep the animal afloat. To do this, the hippo exhales, reducing the air in his body to increase his density.
What is colorimetry?
Because the perception of color is mostly a neurophysiological function between the eyes and the brain, it can vary slightly from person to person. Further, the subtractive color seen depends on the light source. If you plan to paint a room, you should examine the color when illuminated by several different light sources: sunlight, light from incandescent lamps, and light from fluorescent lamps. The colors may look very different. They will even look different in the sunlight at noon versus that near sunset. Scientists, artists, advertisers, and printers need an objective method of specifying color as it relates to the frequency of light.
What is the universal gravitational constant?
Proportionality between gravitational force between two objects and gmm/r2.
What is a converging lens?
A converging lens has at least one convex side. Its shape causes the entering light rays to converge, that is, come closer together. A converging lens can create a real, inverted image that may be projected on a screen. When used as a magnifying glass, it creates a virtual, upright image.
What is current?
Current is the flow of charge. It is measured in amperes, or amps. Named after the French mathematician and physicist André-Marie Ampère, 1775 to 1836. 1 ampere is equal to 1 coulomb of charge passing through a wire divided by 1 second. The greater the voltage difference across the wire, the larger the current.
If the low wavelength light is scattered, why do we only see a blue sky and not a blue, indigo, and violet sky?
Lord Rayleigh, John Strutt, 1842 to 1919, determined that the nitrogen and oxygen molecules in the atmosphere scattered sunlight, allowing us to see the sky. The scattering is strongest at the lowest wavelengths.
Why is AC preferred over DC?
In the late 1880s, Edison and Westinghouse battled over the relative merits of DC and AC power distribution systems. After the electric chair had been developed, Edison attempted to name electrocution Westinghousing because it used AC, but he failed. The AC system was victorious because transformers could raise the voltage to thousands of volts for transmission, then lower it for use in homes and businesses. At the high voltages, the current needed to transmit large amounts of power is reduced. And so is the energy lost to thermal energy, because the heating of transmission wires depends on current and resistance.
What is a fuse?
Protects household electrical circuits are protected by fuses or circuit breakers. Opens when current exceeds a predetermined limit.
What is a diverging lens?
Has at least one concave side. The shape of the lens causes the entering light rays to spread apart when they leave the lens.
What is the ITER project?
International effort to produce electricity from nuclear fusion.
What is a refractor telescope?
Uses one lens to gather, refract, and focus light toward an eyepiece that contains one or more lenses that create an image that the eye can see.
How does the spectrum of a sound relate to its waveform?
Jean-Baptiste Fourier, 1768 to 1830, a French mathematician and physicist. Made discoveries in a number of fields, including the greenhouse effect. He developed mathematical tools known as Fourier series and transforms that are used in a wide variety of applications. The Fourier theorem states that any repetitive waveform can be constructed from a series of waves of specific frequencies, of fundamental and higher harmonics. The reverse is also true if you add together waves of frequencies f, 2f, 3f, etc., specifying their amplitudes. You can construct a complex waveform. Using Fourier analysis, then you can record the waveform of a musical instrument and determine the amplitudes of the harmonics of which it is made, that is, its spectrum. Today Fourier analysis is very easy to do. Most computers either have built-in microphones or can use an external microphone. Free software can be downloaded from the web that will display the spectrum.
What is an open circuit?
Circuit that is open so no charges flow.
What is an interference, destructive?
Two waves, one positive, the other negative that produce a smaller wave amplitude, even zero.
What is the cause of rolling friction?
Rolling friction is the result of deformations of either the rolling object or the surface. Think about how much faster a rolling ball stops on grass or sand than on a hard surface. In those cases the ball has to push down the surface in front of it, which acts the same as contact friction. Or, remember when you rode a bicycle with soft tires. In this case the tire is squeezed when it contacts the street, which also acts like friction.
What is Newton's third law?
When two objects, A and B, interact, the force of A on B is equal in magnitude but opposite in direction of the force of B on A.
What are other uses for microwaves besides communication?
In addition to having a great range of frequencies to transmit information, microwaves are used every day in kitchens around the world. Microwave ovens generate 2.4 GHz waves and scatter them throughout the oven. The microwaves excite water and fat molecules into resonance and cause them to rotate, increasing their thermal energy. Different kinds of molecules absorb the energy at different rates. So some foods are heated more than others. Microwave-safe containers are made of materials that do not absorb microwave energy and so remain cool.
What determines the velocity of a wave?
The velocity of a wave depends upon the material or medium in which it is traveling. Typically, the stronger the coupling between the atoms or molecules that make up the medium, and the less massive they are, the faster the wave will travel. All waves of the same type, transverse or longitudinal, travel at the same speed. For example, a sound wave in air at 0 degrees Celsius will travel at 331 meters per second. Regardless of the sound's frequency or amplitude. Electromagnetic waves can travel either through empty space or through material. Their velocity depends on the electric and magnetic properties of space or the material but not on frequency or amplitude. The velocity of water waves depend both on the properties of the water and on the frequency of the wave.
What is an antenna?
Used to transmit or receive electromagnetic radio waves.
What is indigo?
Indigo is the color between blue and violet in the spectrum, but almost no one can distinguish that color.
In what ways do fluids move?
When fluids move slowly, they exhibit steady or laminar flow. When the speed increases, the flow becomes turbulent. In some cases, laminar flow is desired, in others, turbulent flow is better.
What contributions did Marie and Pierre Curie make?
Marie Sklodowska-Curie, born and raised in Poland, but working in France. Used an electrometer to measure the ionization of the air caused by radioactive minerals. Because the amount of radioactivity produced by a uranium compound depended only on the amount of uranium present, she concluded that the atom itself must be the source. She found that the uranium-containing mineral pitchblende was more radioactive than the uranium itself, and concluded that the mineral must contain a small quantity of another element that was more radioactive than the uranium. Her husband, Pierre, stopped his own work and joined Marie in searching for the element. They started by grinding up 100 grams of pitchblende. But by the time they had found the element, they had processed tons of the mineral. In July 1898 they announced the discovery of an element they named polonium in honor of Poland, where she had been born. In December of the same year they announced they had found an even more radioactive element that they named radium. It took until 1902 for them to separate 1/10 of a gram of radium chloride from a ton of pitchblende. In 1910 Marie announced that she had obtained pure metallic radium. Pierre and Marie shared the 1903 Physics Nobel Prize with Becquerel for their work on radioactivity. Marie won the 1911 Chemistry Nobel Prize for her discovery of polonium and radium. The dangers of radioactivity were unknown when the Curies did their work, but both were affected by it. The radon that was produced when they were processing the pitchblende would have caused lung cancer. But, the leaky windows in their workplace and their frequent bicycle rides in the country spared them. Pierre died in 1906 when he slipped on a wet street and was run over by a horse-drawn wagon. Marie's death in 1934 was due to anemia, known now to be frequently caused by radiation.
What happens to an airplane when it is struck by lightning?
Airline pilots tend to avoid thunderstorms, but when a plane is struck by lightning, the passengers inside the plane are kept perfectly safe. For they are inside a Faraday cage, which shields them from the massive electrical charge. The lightning can, however, disturb and even destroy some of the sensitive electronics used to fly the plane. Studies were performed by NASA in the 1980s in which they flew fighter planes into thunderstorms to see how the planes would react to lightning. The scientists quickly found that the planes actually encouraged lightning, because the planes caused increases in the electric field of the cloud, which in turn caused the lightning to hit the plane's metal body. Studies in the 1980s showed that airplanes actually attract lightning. While lightning storms can still be dangerous, passengers inside airplanes are safe from electric shock because they are actually inside a Faraday cage.
What is a trough?
The lowest point of a transverse wave.
What is the Heisenberg uncertainty principle?
Heisenberg, together with Max Born and Pascal Jordan, tried a totally different approach using mathematical matrices. As part of their work, Heisenberg developed a principle that demonstrates that in the atomic world our knowledge is limited. The uncertainty principle is written as AX equals H/4n. In words, the uncertainty of a particle's position times the uncertainty in its momentum is never less than Planck's constant divided by 4n. If it has a precise location, then its momentum, and thus its speed, measured at the same time, must be imprecise. Planck's constant is extremely small. And so the uncertainty principle is important only for objects the size of atoms or smaller. The position and momentum of a baseball, for example, can both be precisely known at the same time. The uncertainty principle shows why Bohr's electron orbits cannot exist. If you know the radius of the circle precisely, then it must have some velocity along the radius smearing out its orbit. The uncertainty principle also exists in a form linking energy and time. In this form it says that if an electron is in a state that lasts for only a short time, then its energy is not precisely defined.
What is a wave?
A traveling disturbance that moves energy from one location to another without transferring matter.
On a warm day, why do water droplets accumulate on the outside of glasses and soda bottles?
The water does not seep through the container, but instead comes from the air surrounding it. Water vapor is the gaseous form of water that is in air below the boiling point of water. As discussed above, it takes a larger amount of energy to vaporize water. So the molecules of water in the air have more thermal energy than do the molecules in the colder glass. So when the water molecules strike the glass, they transfer much of their thermal energy to the glass. The colder water molecules join together to form water droplets on the glass. The process is called condensation. Condensation also occurs on window panes when the outside is cold and the interior air is warm and humid.
How would lasers produce fusion?
The second method of producing fusion is called inertial confinement. Tiny glass, plastic, or metallic spheres containing about 10 mg of deuterium tritium fuel mixture at high pressure are bombarded on all sides by extremely powerful lasers. The lasers vaporize the sphere, driving a strong inward shock wave that compresses the fuel enough to create fusion. The National Ignition Facility, located at Lawrence Livermore Laboratory in California, has been under construction since 1997. The design goal is to create a 2 megajoule flash of ultraviolet energy that hits the target from 192 separate beamlets. All of the beamlets must strike the target within a few picoseconds. In January 2010, the laser beams delivered 700 kilojoules to a test sphere, heating the gas inside to 3.3 million kelvins. It takes hours for the lasers to cool enough to deliver another pulse. The engineering goal is to deliver one pulse each 5 hours. Before deuterium-tritium fusion fuel can be used, neutron shields have to be built to protect the lasers. There are no accepted engineering plans to convert the energy released to electrical energy. One proposed method is to surround the bead with a blanket of liquefied lithium that would be further heated by the energy released.
How is light emitted?
You undoubtedly have seen the light emitted by hot objects. Whether it is the dull red glow of the heating coil on an electric range or the orange glow of the element in an electric oven or the bright yellow-white of the glowing filament of an incandescent lamp, you have seen light emitted by hot objects. Even the yellow glow of a fire comes from light emitted by hot carbon particles. Energy, usually from stored chemical energy, is converted into thermal energy. That energy is transferred to the surroundings by radiation, including light. Unfortunately, producing light in this way is very inefficient because about 97% of the energy goes into infrared radiation that warms the environment rather than light that can be seen. Because of their large energy use, many countries will be banning incandescent lamps in the next few years. A close-up shot of a transparent LED. LEDs use the same materials as laser pointers and operate more efficiently than incandescent lights. Light can also be emitted by gases and solids. Neon signs are one example of a gas that glows because electrical energy is converted into light energy. High-intensity lamps use either sodium or mercury vapor to produce intense light. Fluorescent tubes and compact fluorescent lamps, CFLs, use electrical energy to excite mercury atoms. The ultraviolet emitted by these atoms causes compounds deposited on the inside surfaces of the lamps to glow. The colors can be chosen to emulate incandescent lamps or daylight. CFLs convert up to 15% of the electrical energy into light. Lasers, mostly used today in CD and DVD players and supermarket barcode scanners and pointers, usually consist of a small crystal composed of a mixture of elements like gallium, arsenic, and aluminium. The lasers produce single-color, intense light that is emitted as a compact ray. The LED lights that are often used as on/off indicators, traffic lights, car tail lights, stop, and turning lights also use electrical energy and the same kind of materials used in laser pointers to produce light that is radiated into many directions. White LEDs that are beginning to be used in home lighting are costly to produce. but are much more efficient and last much longer than incandescent lamps.
What challenges are there in building skyscrapers?
The first challenge is to design a foundation that can support the tremendous weight of a large building. The best way is to dig down to the bedrock. This can be as close as about 21 meters, 70 feet. In New York City to almost 61 meters, 200 feet, in Chicago. If the distance is short, holes can be bored and concrete piers can be formed in the holes. More frequently, a caisson is required. This is a large hollow waterproof structure that is sunk through the mud. Pulling it into and then out of the top of the caisson. A third method is go build a large steel and concrete underground pad that floats on the top of a hard clay layer. The load that the foundation must support includes the weight of the building, its furnishings and equipment, and the changing load of occupants. In addition to the loads, strong winds must also be considered. The walls of early tall buildings were constructed of masonry that supported the weight of the building. The 16-story 65.5 meter, 215-foot, high Monadnock building in Chicago, built from 1889 to 1891, required 1.8 meter, 6-foot, thick walls at the base. It was so heavy that it sank, requiring steps to be constructed between the sidewalk and the ground floor. The second half of the building used a steel frame on which masonry was attached, allowing much wider windows to be used. The steel frames can be bolted, riveted, or welded together. When the 59-story, 279-met 915-foot, tall Citigroup building was constructed in New York City from 1974 to 1977, the frame was bolted together. But later computer models showed that if hurricane-strength winds struck the building, it would be in danger of collapse. As a hurricane moved up the eastern seaboard in 1978, workers hurriedly welded plates over the bolted joints. Luckily, the hurricane moved out to sea, sparing New York. Another effect of winds on tall buildings is to make them sway back and forth. While a variety of braces can reduce the sway, they add weight to the building. Another method is now used. The Citigroup building has a 400-ton concrete damper at the top. The damper moves back and forth, opposing the wind-driven motion of the building and reducing sway. Dampers, both liquid and solid, are used in tall buildings. Towers, offshore oil drilling platforms, bridges, and skywalks. The 210-meter, 690-foot, Burj Al Arab Hotel in Dubai has 11 mass dampers. The dampers can also mitigate the effect of earthquakes. Transporting large numbers of people into and out of upper floors is a challenge too. Those who design the elevator systems, as was demonstrated in the collapse of the World Trade Center buildings on September 11, 2001, stairways can be used in emergency situations. but the simultaneous movement of occupants down and firefighters up the stairways caused severe problems. Another consideration is the safety of occupants in case of fire. Some buildings have entire floors designed to be especially fire resistant, so that people could gather there and be safer than on other floors.
What is a parasitic drag?
Force when an airplane wing, automobile, or any other object moves through a fluid.
What is thermodynamics and statistical mechanics?
Studies how temperature affects matter and how heat is transferred. Thermodynamics deals with macroscopic objects. Statistical mechanics concerns the atomic and molecular motions of larger numbers of particles.
What is compression?
Region of higher pressure in a longitudinal wave.
What is a VAD de Graaff generator?
Device using static electricity to produce very large potential differences.
What can you discover about static electricity? How about exploring the basic ideas of electrostatics?
All you'll need is a roll of cellophane tape. Any brand will do, the cheaper the better. Pull off a strip about 5 inches long, then fold over about 1/4 inch at one end to serve as a handle. Press the tape on your desk or a table. Mark the strip with the letter B. Make a second identical tape, and press it down next to the first. Holding the two tapes by their handles, quickly pull them off your desk. They'll probably be attracted to your hands, so shake them until they hang free. Then bring them closer together. What do you see? You should see them bending, evidence that there is a force between them. If they don't bend, stick them on the desk again and again, pull them off. Do they provide evidence that there is an attractive or repulsive force between them? Well, say that pulling them off the table caused them to be charged. Although we have no evidence with what they are charged. They were obviously charged in the same way. So we can conclude that objects with like charges repel each other. By the way, well, work toward an explanation why they're attracted to your hands. Press the two strips back on your desk. Now make 2 more strips the same length and press them on top of the first 2 strips. Mark these strips T to identify them as the top tapes, as opposed to the B or bottom tapes. Slowly pull the T and B pair of tapes off the desk together. If they are attracted to your hand, then use the other hand to gently pat both sides of them over their entire length. That should remove any residual charge from the pair of tapes. If not, pat them down again. You have a pair of objects with no charge. Holding the two handles of the pair, rapidly pull them apart. Again, if they are attracted to your hands, shake them until they hang freely. Bring them closer together. Is there evidence of a force between them? Is it attractive or repulsive? You started with a pair of objects with no charge. Pulling them apart caused them to be charged, but not in the same way. Because they didn't repel each other, but attracted. Thus you can conclude that they must be charged differently, and objects with different charges attract. To keep your charged tapes, you can hang them from the edge of your desk or a desk light. Make a second T and B pair and see if the two top tapes are charged alike or differently. If the tapes stop interacting, you can repeat the charging procedure as often as you like. Hang a T and a B tape so you can bring objects near them to see if there are forces between them. Make a list of the objects you tried and whether they attracted or repelled the T tape and the B tape. Try your finger. Then try rubbing a plastic pen on a piece of wool. Try plastic rubbed by silk or polyester. Try glass and metal. Do some objects attract both tapes? Repel both tapes? Attract one and repel the other? If they do the latter, you can characterize them as being charged like the T tape or like the B tape. Well, come back to understand why some objects can attract both kinds of charge, but no objects can repel both.
Why is your blood pressure taken from your upper arm?
Liquid pressure is dependent on the depth of the fluid. Since blood pressure can't be measured around the heart, and the depth of the fluid must be the same as the heart, doctors and nurses need to find a location at the same depth as the heart. A convenient location at that level is your upper arm. When lying down, however, your blood pressure can be taken just about anywhere. Since most of the blood is at the same vertical level as the heart, the cuff is inflated until no pulse can be heard. It is then slowly lowered. As the pressure falls below the systolic pressure, the pulse can be heard. When it's below the diastolic pressure, the pulse gets weaker. The report 120/70 means that the systolic pressure is 120 torr, the diastolic pressure 70 torr.
How could you arrange the location of the pivot to make the mechanical advantage less than 1?
Look closely at a pair of scissors. Note that you can adjust the mechanical advantage by moving the region of the scissors you are using to cut.
What is Bernoulli's principle?
In 1738, a Swiss physicist and mathematician named Daniel Bernoulli, 1700 to 1782, discovered that when the speed of a moving fluid increases, such as the wind blowing through the corridors of a city, the pressure of that fluid decreases. Bernoulli discovered this while measuring the pressure of water as it flowed through pipes of different diameters.
What is a refraction?
Bending of light as it goes from one medium to another.
How much resistance do our bodies have to electrical current?
On average, the human body has an electrical resistance between 50,000 and 150,000 ohms. Most of this resistance is across the skin. If the skin is wet, the resistance drops to about 1000 ohms. If the skin is broken, then resistance across organs in the body is on the order of a few hundred ohms. In this condition 10 volts is sufficient to cause serious, if not fatal damage.
What is a second, S?
The time it takes for 9,192,631,770 periods of microwave radiation that result from the transfer of the cesium-133 atom between lower energy and higher energy states.
How did the idea that the Sun was the center of the solar system arise?
Aristotle's and Ptolemy's view that the Sun, planets, and stars all revolved around Earth was accepted for almost 18 centuries. Nicholas Copernicus, 1473 to 1543, a Polish astronomer and cleric, was the first person to publish a book arguing that the solar system is a heliocentric, sun-centered system instead of a geocentric, Earth-centered system. In the same year as his death, he published On the Revolutions of the Celestial Spheres. His book was dedicated to Pope Paul III. The first page of his book contained a preface stating that a heliocentric system is useful for calculations, but may not be the truth. This preface was written by Andreas Osiander without Copernicus' knowledge. It took 3 years before the book was denounced as being in contradiction with the Bible, and it was banned by the Roman Catholic Church in 1616. The ban wasn't lifted until 1835.
When a solar eclipse occurs, is the entire Earth in the Moon's shadow?
The shadow of the Moon only covers an area of about 300 kilometers in diameter. This shadow, the umbra, moves along a path of Earth's surface at about 1000 miles per hour. In the penumbra a partial eclipse is seen, but even this path is quite narrow.
What is an image, light?
Point at which light rays converge.
What is retina?
Screen on back of eye. Has cells that detect light and a neural network that does preliminary processing of the information received.
What is a solar eclipse?
Occurs when the Moon casts its shadow on Earth. The Moon must be directly between the Sun and Earth.
How can the acceleration be independent of mass? Doesn't a bowling ball fall faster than a soccer ball? Which weighs more, the bowling ball or soccer ball?
You can use your hands to hold first one ball and then the other. You'll notice that you have to exert a much larger upward force to hold the bowling ball at rest. From Newton's first law. If an object is at rest, then the net force on it is zero. That is, the downward force of gravity has the same strength as the upward force of your hands. So, you can conclude that the force of gravity, the weight of the bowling ball, is greater than that of the soccer ball.
What is the law of reflection?
Angle of incident light is equal to angle of reflected light.
What is a British thermal unit, BTU?
Unit of energy often used to measure heat in homes and industries.
What are quark generations?
Each generation has two quarks, up and down in first, strange and charm in second, top and bottom in third.
What is the chemical energy?
Potential energy of a system due to its chemical composition. A chemical change can cause this energy to be changed into or out of other forms. Animal bodies and batteries are two common objects that have chemical energy.
What is heat conduction?
Occurs when two objects are in contact, like when you put your hand in hot water.
What does Kepler's third law tell us about the motion of satellites around Earth?
Kepler's third law relates the period of a satellite to its distance to the center of Earth. The table below shows the mean radius of the orbit, the altitude above Earth's surface, and the period for some typical satellites. Whether satellites have polar orbits so that the view of their cameras sweeps across the entire surface of Earth many times each day. The Moon's orbit is aligned with Earth's orbit around the Sun, not Earth's equator. Kepler's third law holds for satellites about other planets and for planets revolving around the Sun. But you need either Newton's laws or Einstein's relativity theory to explain these results.
What major discovery did Archimedes make in the 3rd century BCE and how did he apply it?
Archimedes, c. 287 c. 212 BCE, lived in the city of Syracuse on the island of Sicily, then part of Greece. He was charged by the king of Sicily to find out if his crown was made out of pure gold, or an alloy of gold and silver. Archimedes had to do this without destroying the crown. One day, when bathing in the public baths, he noticed that when he stepped into the bath the water rose. He had seen this many times before, but this time he recognized that this common occurrence could help him solve his problem. Legend has it that he was so excited that he ran naked through the streets of Syracuse, shouting "Eureka!" or "I have found the answer." He then did experiments where he hung the crown on one end of a balance and a piece of first gold and then silver from on the other end. When the weight of the crown and that of the metal were equal, the balance was horizontal. He then immersed the balance in water. If the crown and the metal had different volumes, the water they displaced would be different and the balance would tip. He found that the balance tipped when both the silver and gold pieces were on the balance. Archimedes had found that the crown was not pure gold, but a mixture of silver and gold. The king had been cheated. Archimedes had discovered a principle of hydrostatics, liquids at rest, that would one day carry his name. Archimedes' principle states that an object immersed in a fluid will experience a buoyant force equal to the weight of the displaced fluid. A huge steel ship like an aircraft carrier can float instead of sink like a stone, because it can displace enough water to compensate for its weight and because the air inside of the ship makes its density actually less than the water around it.
How much charge is inside the sphere of a Van de Graaff generator?
0. When negative charges leave the rubber belt, they move immediately to the outer surface of the sphere. Negative charges like to be as far away from each other as possible. So they move to the outer surface of the Van de Graaff generator's sphere. An old, damaged photograph of British physicist Michael Faraday, who was the first to describe an electric force in terms of a field. He also invented the Faraday cage, which permits electric charges on the outer shell but not within the cage itself.
Does Benjamin Franklin's definition of positive and negative agree with today's understanding of charge?
Franklin decided that sparks given off by an object charged by a glass rod, vitreous electricity, looked more like fluid leaking out than did the sparks from an object charged by a rubber rod, resinous electricity. Thus he decided that glass had an excess of electrical fluid. Today we know that electric charge is mostly carried by electrons. Electrons are charged the same way that rubber or plastic is, negatively. Thus we say that they have a negative charge, because they are transferred much more easily than are the more massive, positively charged nuclei. When there is an excess of electrons, the object is negatively charged. When there is a lack of electrons, it is positively charged. So even though Franklin made the wrong choice, we still follow his convention.
What is the Doppler effect?
The Doppler effect is the change in frequency of a wave that results from an object's changing position relative to an observer. A well-known example of the Doppler effect is when an ambulance zooms by you and makes a wee-yo sound. The high-pitched wee is caused by sound waves that are bunched together. Because the ambulance is moving in the same direction as the emitting sound waves, the bunching together of sound waves creates an increase in the frequency and results in a higher pitch sound. The low-pitched yo sound occurs when the vehicle moves away from the propagation of the sound wave. Since the ambulance moves away from the sound wave, the spacing between successive waves becomes greater. This decrease in the frequency of the sound wave results in a lower pitch.
How is the gravitational field related to force?
As was described above, the force of gravity on an object is equal to the object's mass times the gravitational field strength, expressed as F equals mg. Thus if you have a mass of 70 kilograms, 154 pounds, the force of gravity on you is 686 newtons. Mass has been defined both in terms of acceleration and gravitational force.
Who was the first person to explain how rainbows are formed?
Newton was not the first person to understand the optical characteristics of a rainbow. In fact, it was a German monk in the early 14th century who first discovered that light refracted and reflected inside a water droplet. To demonstrate his hypothesis, the monk filled a sphere with water, sent a ray of sunlight through the sphere, and observed the separation of the white light into colors along with the reflection on the back of the water droplet.
What kind of forces can you exert on an object?
Hold a book in your two hands. What kind of forces can you exert on it? You could pull on the book to try to make it longer, or you push it to try to make it shorter. The name for the force on the book that pulls on it is a tension force, while the name for the force that pushes on it is a compressive force. You could also try to twist it, applying what is called a torsional force. Finally, place one hand on the front cover and the other hand on the back cover. Now push one hand to the right and the other to the left. This places a shear force on the book. Tension forces are common. If you hang from a chin-up bar, your arms experience a tension force. Pulling on a rope, wire, or cable also exerts tension on them. Materials experiencing tension will stretch some more and some less. Materials that stretch easily are called pliant, those that do not are called rigid. Scientists have measured the response of materials to tension and compression. The ratio of the applied pressure, called stress, to the change in length divided by the original length, called strain, is called Young's modulus. Its value varies from 10 Gn/m to 10 billion newtons per square meter. In wood to 200 Gn/m2 in steel and cast iron. That means that for an equal force on it, steel will stretch, or compress, 1/20th as much as wood. If you would hang a 120 kilogram, 264 pound, ball from a 6 meter, 19.7 feet long steel cable 2.5 millimeters, 0.9 inches, in diameter, it would stretch 7 millimeters, 0.3 inches. In the case of the cable above, when you remove the weight, the cable will return to its original length. It is called an elastic material. If you exert a much larger force, the cable will not return to its original length. This is called the plastic region. At some point it will break. The force that breaks it is called the tensile strength. For steel, the tensile strength is 1 Gn/m2. Thus for cable in the example above, it would take a hanging mass of 500 kilograms, 1,100 pounds, to break the cable. Young's modulus also describes the change in length of an object when a compressive force is exerted on it. When you stand, you exert a compressive force on your leg bones and they will shrink somewhat in length. But a 70 kilogram, 154 pound, person standing on one leg will compress it by only 0.01% of its length. The Young's modulus for cartilage, the material between the bones in all parts of your body, is 1/10,000th as large as that of bone. So putting the weight of a 70 kilogram, 154 pound mass on a piece of cartilage with same area as the femur in your leg would compress it by 10% of its original thickness. For compressive forces there is a compressive strength. But, many materials will buckle if too great a compressive force is placed on it. Brittle materials will, on the other hand, break. The compressive and tensile strength of bones is almost exactly the same.
How do cell phones work?
Cell phones use the UHF part of the electromagnetic spectrum. 800 to 900 MHz, 1700 to 1800 MHz, and 2100 to 2200 MHz. The service area for a cell phone provider is divided up into hexagonally shaped cells, each one served by base stations with antenna towers at 3 corners of the cell. The stations can both receive and transmit information to cell phones. The stations are connected to a network that uses fiber optic cables. When a cell phone is turned on, it searches for available services according to a list stored in the phone. It selects the correct frequencies to transmit and receive data, then sends its serial and phone numbers to the system, registering itself in that cell. The network makes sure that the phone number is part of its system and that there is money in the account to pay for a call. After registration is complete and a call is made to that phone, the network can direct the call to the correct cell. The cell phone always searches for the strongest signal from a tower. If the phone moves during the conversation, then the signal strengths will change and the phone will hand off the call to a different base station. The technology behind the cell phones we take for granted today is amazing. Transmitting and receiving messages in the electromagnetic spectrum. Cell phones automatically select and correct appropriate frequencies, send serial numbers to servers, and register themselves in the cell in which they are located at the time. Cell phones digitize the voice signals. Special circuits, called digital signal processors, then compress the voice signals and insert codes that can detect errors in transmission. Compression is achieved by sending only the changes in the digital signals, not what stays the same. Cell phone systems also send many different conversations at the same time. One method, called TDMA, time division multiple access, splits up 3 compressed calls and sends them together. CDMA, code division multiple access, uses TDMA to pack 3 calls together, and then put 6 more calls at 2 other frequencies. Each of the 9, or more, calls is assigned a unique code so that it can be directed to the correct recipient. Spread CDMA systems use a wide band of frequencies that permit more simultaneous calls.
What is the history of measurements of the speed of light?
In 1638 Galileo, 1564–1642, proposed a method of measuring the speed of light. Galileo would have one lamp and an assistant a great distance away would have a second lamp. The assistant was to uncover his lamp immediately when he saw Galileo uncover his own lamp. The speed could then be determined by measuring the time it would take the light to travel from Galileo to the assistant and back again. Galileo claimed to have done the experiment several years before 1638, but there was no record of his results. In 1667 the Academy of Sciences in Florence, Italy, carried it out between two observers a mile apart. They reported there was no measurable delay, showing that the speed of light must be extremely rapid. The first measurement of the speed of light in a laboratory was by Hippolyte Armand Fizeau. 1819–1896, in 1849. He used a beam of light that passed through the gaps between teeth of a rapidly rotating wheel. Was reflected from a mirror 8 kilometers away, and returned to the wheel. The speed of the wheel was increased until the returning light passed through the next gap and could be seen. The speed was calculated to be 315,000 kilometers per second. Leon Foucault, 1819–1868, improved on this a year later by using a rotating mirror in place of the wheel and found the speed to be 298,000 kilometers per second. He also used this technique to determine that light travels slower in water than in air. The American physicist Albert Michelson, 1852–1931, greatly improved Foucault's measurement. Using an 8-sided rotating mirror and a plane mirror located on Mount San Antonio, 35 kilometers, 114,800 feet, away from the source on Mount Wilson in California. By measuring the speed of the rotating mirror and the distance between the mirrors, Michelson made the most accurate measurement of the speed of light to that date. In 1907, he was honored by being the first American to win the Nobel Prize in Physics. In 1926 he made a new measurement that yielded 796 kilometers per second with an uncertainty of 4 kilometers per second. After Maxwell published his theory of electromagnetism, it became possible to calculate the speed of light indirectly from the relationships between an electric charge and its electric field and an electric current and the magnetic field it produces. In 1907 Rosa and Dorsey obtained 299,788 kilometers per second in this way. The uncertainty of 30 kilometers per second made it the most precise measurement to that date. Research on microwaves used in radar during World War II led to a new method of measuring the speed of light. By 1950 Louis Essen reported a result of 299,792 kilometers per second. Slightly more precise than Michelson's result. In the 1970s, scientists at the National Institute of Standards and Technology in Boulder, Colorado, succeeded in directly measuring simultaneously the wavelength and the frequency of an infrared laser. From these two measurements they could calculate the speed of light. 299,792.4562 km per second with an uncertainty of only 1.1 meters per second. This new technique prompted an investigation of the length standard. The wavelength of light from the gas krypton. The new techniques discovered that the standard was fuzzy and had to be replaced. In 1983 the Conference Générale des Poids et Mesures decided to fix the speed of light in a vacuum at 299,792.458 km per second and define the meter as the distance light travels in 1/299792458 of a second.